Okay, so today we're going to go ahead and talk about net torque and how it relates to angular acceleration. Okay, so first off, I want you to remember from the beginning of the year, we talked about Newton's second law a lot. F net equals ma. So again, sum of all the forces equals the mass times acceleration. Now when we deal with rotational motion, we're going to have a rotational analog to this equation. So I want you to take a guess what this equation is and then check back into the video. Okay, so F net. So that's a force. Now we're going to deal with a force that makes things rotate. A force that makes something rotate is just going to be a torque net. Again, just one torque, but we're dealing with F net, so we're going to have to deal with torque net. Equals the rotational analog to mass is going to be moment of inertia. And instead of linear acceleration A, we're going to have angular acceleration alpha. Cool. Let's go ahead and think back just to remember our equation. So this is the big equation we are going to deal with for a couple days. So our other, just as a quick reminder, if we have a torque, again, a torque is a force that makes something rotate. So it's some force that is perpendicular to some rotational arm, and r is the distance from the radius to where you're applying that force. So again, if I were to have like just a little example, so let's say here's our pivot, and here is our force. Our torque would be F times R, because F is totally perpendicular. If it's not 100% perpendicular, you will have to find the perpendicular part of F. Okay, so let's go ahead and solve the problem together. Let's go ahead and do the problem below. So I would encourage you to try this problem yourself and then check back into the video. Okay, so let's go ahead and look at this problem. So we have 200-gram model rocket, and it generates 4 newtons of thrust. Okay, so here's our rocket. We have 4 newtons of thrust. It spins in a vertical circle at the end of a 100-gram rod. What is its angular acceleration? Okay, there's going to be a lot to this problem. So what let's do, and again, I took this problem from the Tnet textbooks. It's a great textbook. So let's see. So first, what I want to do, we're gonna use this equation. We want to find angular acceleration and forces are acting on it. We're going to use this new equation, Tnet equals I alpha. So first thing I want you to do is go ahead and find the moment of inertia of this whole system. So I'm going to say find I. Go ahead and try it yourself. Check back in on the video. Okay, so to find I, I'm going to go ahead and label the pivot point. So that's our pivot point. We have both a rod and we have a rocket. So to find the total moment of inertia, I am going to add those things together. So the moment of inertia of the rod plus the moment of inertia of the rocket. So the rod is rotated about the end, so we know that is going to be 1/3 ml squared. And the rocket is just a point mass at the end, so that is going to be mr squared. Okay, generally when I do these problems, when I'm dealing with newtons, I'm going to want things in meters and kilograms. So let's make sure we convert as we plug things in. So the rod has a mass of 100 grams, which is 0.1 kilograms. The length of the rod is 60 centimeters or 0.6 meters. The mass of the rocket is 200 grams, which is 0.2 kilograms. And then the radius is the distance from the rocket to the pivot is 0.6. Cool. Plug it into my handy dandy calculator and I get I, which is 0.084 kilogram meter squared. Okay, cool. So we got I. So now let's go ahead and find the net torque. So first let's go ahead and draw all the things that cause it that our force is acting on. So we have the force of the thrust, which is 4 newtons. We have force of gravity acting on the rocket, which is what, 0.2 kilograms? So that is just going to be 2 newtons down. And then we have force of gravity acting on the rod. So let's draw again. The force of gravity needs to act from the center of mass of the rod. So that is just going to be straight down like that. So it's a 100-gram rod, which is 0.1 kilograms. So it's a 1 Newton force for the rod. Cool. Okay, so let's look at the end of this rod. So we know there's 4 newtons going up, 2 newtons down, applied the same distance from the pivot point. So I'm going to call that is like a net 2 newtons going upwards is F net at the end of the rod. Okay, so let's see what this force is exerting for a torque. So this force is not just perpendicular to the rod or just parallel. It's a little of both. So we're going to have to split it into the perpendicular and parallel parts. This right here is going to be the perpendicular component of the rod. So F perpendicular is going to be 2. We have to look across from that. So 2 sine of 45 degrees is going to be the perpendicular part. Which I got when I put it in, I got 1.41 newtons to be the perpendicular component of this net force. And again, that was just combining the 4 newtons of thrust and 2 newtons of gravity to find our Fnet. Okie dokie. So let's see, what torque does that exert? So the torque at end is going to be the force perpendicular at the end times the distance of the pivot. So that is just going to be, let's see, I should make a little more space. That's just 1.41 times the distance from that force to the pivot is the whole length of the rod, which is 60 centimeters, which is 0.6 meters. And so that's 0.85 Newton meters. Okay. So now let's go ahead and try another. So we have, that's the torque at our end. So now, and that's going to make it rotate. So I'm going to start writing my net torque. That is going to make it rotate counterclockwise, which I will call counterclockwise in negative direction. So I'm going to say we have 0.85 Newton meters. So this is torque at end. And counterclockwise, again, that makes it rotate. So now let's go to the other part. So we split this force into the X and Y, and again, that's a 45-degree angle. This part right here is going to be the perpendicular part. So that's going to be I should write that down here. So that is going to be force of perpendicular is going to be 1 cosine of 45 degrees, which is 0.707 Newton. Okay, so now if we plug that into our torque equation, it's going to be the force times the distance of the pivot, which the force is 0.707, and the distance from the pivot is here to here, which again, we drew that force of gravity vector on the middle center of mass of the rod, which that is 30 centimeters away from the pivot, which is 0.3 meters. So now we can multiply 0.707 times 0.3, and I get 0.212 Newton meters. And again, that will make it rotate clockwise. So that is going to be, that's going to be a positive direction, plus 212 Newton meters. And that makes sense that that force is smaller than the other one because the rocket thrust generating is likely going to make it spin in that direction, which is going to be counterclockwise, while gravity's fighting a little bit against it. Cool. So we got our net torque. And I got negative 0.638 when I plug that all in. Okay. So now we have, so that's our Tnet. Okay. So now let's see what we can plug in for Tnet equals I alpha. So we got, let's again write down our equation. So Tnet equals I alpha. So we got the torque net to be negative 0.638. We got the moment of inertia earlier. We calculated that in the black writing. That is 0.084 alpha. We can divide both sides by 0.084 and we get alpha. And I get negative 7.59 radians per second squared. And again, if you chose like the opposite direction to be positive, you get a positive number. Oftentimes it's usually the magnitude that matters. Cool. Well, thanks for watching. I'll go ahead and go through 2 more examples just for fun. But otherwise, this is great. Okay, so let's go ahead and try a couple other problems involving Tnet and moment of inertia and angular acceleration. So we have, imagine these objects, so they're free to rotate about the point X, and their point masses connected by rigid massless rods. So any of the rods connecting the masses have no mass at all. So we just have to worry about the masses themselves. Okay. So imagine it's like something, these things are like suspended in the air. So this one right here is suspending vertically in the air. I want you to think about, for example, A, what is the angular acceleration? And then check back into the video. Okay, so let's look at it. For this 4 kilogram, you have gravity pushing downwards on it. Force of gravity is going to be 40 newtons. You also have gravity on the 7 kilogram, which is pushing down 70 newtons. So let's see, what torque is this 4 kilogram one going to exert about the pivot? So what I think of is if you hold your pencil vertically or pen and you push down on the eraser or the end of it, is that going to cause it to rotate? No, that's not going to cause it to rotate at all. Like if you're pushing straight down that direction, that's not causing it to rotate because that is the distance from the pivot. Those two are parallel, so the torque to that one is 0. Or if you, again, hold your pen or pencil vertically and pull at the bottom of it, is that going to make it rotate? Nope, not at all. So the torque on the bottom is just going to be 0. Okay, so cool. So then if we add that all up, the net torque is going to be 0, which if the net torque is 0, there is no angular acceleration, and that is just going to be 0 radians per second squared. Cool. Let's go ahead and look at the next example, B. So let's do the torques first. So we have this 5 kilogram is pushing downwards with a force of 50 newtons. let's see, it is 3 meters away from the pivot. So the torque is going to be 50 times 3. And again, the force and distance from the pivot are perpendicular, so that is going to create a torque and make it spin. What would that be? Clockwise. So that's going to be 150 Newton meters clockwise. Let's look at the other one. This 3 kilogram mass is pushing down with 30 newtons of force. The torque is going to be 30 newtons times 2 meters, which is going to be 60 Newton meters clockwise. Cool. So then the net torque, those are both making it rotate clockwise. So we just add those together, and that is going to be 210 Newton meters. Okay, let's go ahead and also find the moment of inertia for this. I'm going to do moment of inertia in a different color. So inertia is going to be, again, these are masses connected by massless rods, which we're going to use point masses for that. That's going to be m1r1 squared plus m2r2 squared. So we're going to have 3 times distance of pivot 2 squared plus 5 times how far away is that from the pivot? 3 squared. And that is, I got 57 kilogram meter squared. So let's go ahead and plug that into our T net equals I alpha equation. So let's see, we have T net, and again, this is for B. We have T net equals I alpha, the torque net is 210, moment of inertia is 57, and we want to find alpha, and I get alpha to be, what is that, 3.68 radians per second squared. Cool. Go ahead and try the next one yourself and then check back on the video. For the last one, I got 2.98 radians per second squared for my answer for C. But I'll go ahead and quickly go through it right now. So let's see. This one right here provides a force of 50 newtons. How far away is it from the pivot? That is 3 meters from the pivot. So the torque is going to be, what, 50 times 3. So that's 150 Newton meters. And that would make it rotate clockwise. Let's see, this one right here, force of gravity is 30 newtons. Torque would be, what, 30 times 2, which is 60 Newton meters. And again, that's clockwise. Let's go ahead and look at the last one. So we have 70 for the FG, and then the torque is the force times distance from the pivot. So 70 times 0.5, which is, sorry, I got a little update. I'll take that off. Okay, so that's what, 35 Newton meters, and that would make it rotate this way, which is the counterclockwise direction. So I'll call the clockwise ones positive and the counterclockwise ones is negative. So T net is going to be 150 plus 60 minus 35, and I got 175 Newton meters for T net. Let's go ahead and find moment of inertia real quick. So inertia, again, that is like the total mass of the system. I want you to remember, inertia, more mass something has, it has more inertia. So we're always going to add when we are calculating moment of inertia. So we have 3 masses in this case, all connected by massless rods. So we are going to use our point mass formula. Gosh, I love the point mass formula. It's so fun. I'll call the left one M1. So what, 7 times 0.5 away from the pivot. The other one is 3 times 2 from the pivot. This 5 kilogram. And again, it's how far it is from the pivot. How far is that from the pivot? Not 1 meter, but 3 meters. Cool. And let's see, what do we get? I get 58.75 kilogram meter squared. Cool. So now we go ahead, I'll do it in a different color. Our last little step where we plug everything in to T net equals I alpha. I write down the equation, you get points for that. It also helps avoid some mistakes. So T net was 175. We got what? 58.75. Alpha, we divide both sides by 58.75, and I get 2.98 radians per second squared. And that, my friends, is our answer. Thank you so much for watching these torque videos.